Hey there, this is Aero421 Group 2, and we will be presenting about control moment gyroscopes, singularity avoidance, and steering logic. This presentation was made by Dominic Chung, Connor McQueen, Samuel Brand, Emmett Allen, and Bridget Peterson. So moving on to the first slide, just to get a quick introduction, control moment gyroscopes, also known as CMGs, are devices used to control a spacecraft's attitude, similar to other momentum exchange devices such as the reaction wheel. Within the subcategory of CMGs, there exists their own design variations. And with devices like these, a problem to look out for is gimbal lock. This is an event that can happen with any of the aforementioned devices. And to move on to the next slide, gimbal lock effectively removes one of the spacecraft's degrees of freedom by taking control away from rotating on one of the spacecraft's three axes. You can see from the pictures on the right that gimbal lock caused quite a scare during the Apollo 13 mission.
Houston, we have a problem.
During the quadruple failure reading, the spacecraft was flying close to gimbal lock due to an instrumentation failure. This is also the infamous Houston, we have a problem scene.
Houston, we have a problem.
Multiple control strategies have since been implemented on various missions to prevent gimbal lock, and we will be discussing these later on in the presentation. And now I will be introducing Samuel Brand to discuss the similarities and differences between reaction wheels and CMGs.
To compare a control moment gyro to other momentum exchange devices, I'm going to outline the key differences between a simple reaction wheel, which will take the place of any other momentum exchange device, and a CMG. So on the left side of the chart, we can see a reaction wheel, and this image basically illustrates how a reaction wheel works, where it has a constant spin axis parallel to the axis of symmetry of the wheel with a motor to vary the spin rate. So like I said, the mechanism consists of a motor and a wheel, where the motor spins the wheel, which in turn increases or decreases the momentum of the wheel based on the applied spin rate. And this momentum change will result in the spacecraft imposing an opposite torque due to the reaction wheel. And so to provide stability about multiple axes, using reaction wheels, it is common to have clusters of reaction wheels oriented about different spin axes, since like I said before, the spin axis is fixed. So you'll see them in a cluster where you'll have multiple facing in different directions at different angles in order to try and provide stability in multiple different directions. So similar to the reaction wheel, the CMG mechanism consists of a motor and a wheel, except in this system, the spin rate is kept constant, while a gimbal is used to change the direction of the rotation axis. So we can see how the CMG uses gimbaling to vary the spin axis of the reaction wheel. So this change in rotation axis direction will result in a change in direction of the angular momentum of the wheel. And so this in turn will cause the spacecraft to change its momentum in order to conserve the net angular momentum of the system. So a similar sort of mechanism as to the first one, but instead of varying the rotation speed, we're gimbaling it to change which axis it's rotating about. And so overall, based on before, the reaction wheels are simpler, less expensive, and often have longer lifespans with lower mass, volume, and power requirements as compared to the CMG, just due to its complexity. But the thing is, they're limited by the motor's torque, while CMGs will produce higher torques, which will result in a quicker spacecraft maneuvering. But due to the changing momentum vector, singularities may occur, otherwise known as gimbal lock, which Connor will explain next.
Gimbal lock is the condition in which, when using Euler angles, two of the Euler axes become aligned, and the ability for command input into one or more of the axes will fail to yield the desired angle changes. For example, with this diagram of a gimbal system, we have three Euler axes of rotation. X, Y, and Z, or yaw, pitch, roll, are represented by these red, green, and blue rings. Red being X, or yaw, green being Y, or pitch, and blue being Z, or roll. Using this system, if we have a 90-degree pitch change, you can see that the X ring is now aligned with the Z ring. In this configuration, there's no way for the cube to tell the difference between a change in the blue Z ring and the X ring. This is what is known as gimbal lock. Nothing is physically constrained or locked, but a combination of controls must now be implemented in order to separate the aligned axes and enact a roll maneuver. For example, with this diagram of an aircraft, in order to cause a roll of the aircraft, the y-axis would now have to be pitched down and rotated.
Variable speed control moment gyros can also be used to prevent singularities. Variable speed gyros function similarly to reaction wheels. In both devices, changing the speed of the rotor creates a torque on the spacecraft. In a control moment gyro, this torque adds another degree of freedom to the system, in addition to the gyroscopic torque created by the gimbal. This can be used to introduce torque from another direction during attitude maneuvers to avoid a singularity. To reiterate on what Sam said regarding momentum wheels and control moment gyro advantages and disadvantages, a control moment gyro is ideal for control problems that require large torques, such as on large spacecraft or for attitude control in high external torque environments. This relates to control strategy because control moment gyros are less accurate than other control means and are often great for quickly changing a spacecraft's orientation and rotation, but not for achieving accurate pointing. More often, momentum wheels are used for finer degrees of pointing accuracy, but cannot be used to achieve the large torques control moment gyros produce. This is because momentum wheels would either have to be unreasonably high in mass and size for a given system, or would have to use an unreasonable amount of power. Magnetorquers are often used for extremely fine pointing accuracy, less than 20 degrees, but this is because they produce very small torques. A combination of these systems is best for achieving both accurate and rapid pointing. Multiple novel control laws have been created to avoid singularities and to maintain control when operating near singularities. The one-step-ahead singularity index strategy creates a function to measure how close to a singularity a future state will be, and minimizes this function to prevent singularities. When approaching a singularity, error will be introduced into the Euler angle calculations over time. Predicting this error in advance of live data is necessary to avoid autonomous error-based attitude adjustments that may result in wasted power or longer detumble times due to a decrease in algorithm accuracy. The artificial potential function uses null motion, that is, motion of the gimbals independent from motion of the spacecraft, to avoid singularities. It uses known gimbal-based attitudes to determine safe target attitudes and treats singularities as targets for avoidance. Creating maneuvers that avoid error from singularity approach as much as possible. While the equations are given for these laws, breaking these down further is beyond the scope of this video.
In conclusion, control moment gyros are momentum exchange devices rather than reaction-type actuators, such as propulsive devices. Reaction-type actuators are often less reliable than internal control devices and often result in shorter mission life as propellant is limited in quantity from the start of the mission, making control moment gyros advantageous for longer missions. Control moment gyros are similar to reaction wheels as both devices create a torque on the spacecraft. They are ideal for large spacecraft as the torque produced is rather large in comparison with reaction wheels and magnetorquers. One challenge of using control moment gyros is gimbal lock, which occurs when two rotational axes align. A degree of freedom is removed, resulting in a singularity, and requiring added software complexity via novel control laws and algorithms. Variable speed control moment gyros in particular can be used to add degrees of freedom, though they are more expensive. There are always many trades to consider when designing an attitude control system, and a fundamental understanding of control moment gyros is necessary to design control systems.
Well, between Jack's back taxes and the Fred Hayes show, I'd say that was a pretty successful broadcast.